A single, invisible force is tearing our universe apart. This force is called dark energy, and it makes up most of everything that exists. By the end of this exploration, you will understand how this mystery reshapes our cosmic destiny and why its discovery turned science upside down. We will see how a simple, distant flicker of light betrayed a universe accelerating toward a cold, lonely end. And we will confront theories that suggest everything from a silent hum in empty space to a phantom menace waiting in the future. What does it feel like to live in a universe dominated by something we cannot see? The universe was a story with an ending everyone thought they knew. For decades, the grand cosmic narrative was one of a magnificent but fading expansion. The immense explosion of the Big Bang had set everything in motion, hurling galaxies away from one another into the vast dark. Yet, scientists were confident that the story's final chapter was already written by a familiar force, gravity. Think of a firework bursting against a night sky. For a glorious moment, the embers fly outward in all directions, but then, inevitably, they begin to slow. Each spark feels the tug of the planet below, and they all fall back toward the ground. This was the expected fate of our cosmos. The collective gravity of every star, every galaxy, every speck of dust was thought to be acting like a cosmic brake, gradually slowing the universe's great rush outward. The ultimate destiny, many theorized, could be a dramatic reversal, a cataclysmic collapse back in on itself in a fiery big crunch. This view was not mere speculation. It was built upon two pillars of modern science. The first was the revolutionary observation by astronomer Edwin Hubble in the 1920s. By carefully studying the light from distant galaxies, Hubble noticed a profound pattern. The farther away a galaxy was, the faster it appeared to be moving away from us. This was the first direct evidence that space itself was stretching, that the universe was not static but actively growing. The second pillar was Albert Einstein's theory of general relativity, a breathtakingly elegant framework that described how matter and energy shape the very fabric of space and time. Einstein's equations could model the entire universe, and for most of the 20th century, they seemed to describe a cosmos expanding from a hot, dense beginning, gradually coasting to a stop under its own weight. It was a comfortable, almost intuitive narrative, one where the laws of physics as we understood them held complete sway. This established view created a powerful sense of predictability. Astronomers measured the expansion not to see if it was slowing, but to measure precisely how fast that slowdown was happening. They were confident they were simply filling in the details of a story whose plot was already settled. Little did they know, they were measuring the wrong thing entirely, and the universe was about to reveal a twist that would shatter this comfortable narrative and send physicists back to their drawing boards in a state of bewildered awe. The data from those distant supernovae began to tell a story no one was prepared to hear. Astronomers were using these stellar explosions like cosmic mile markers, precisely placed across the deep sky. A Type 1, a supernova, is a special kind of event. It occurs in a binary star system where a dense white dwarf star steals material from its companion. Once it reaches a very specific critical mass, it detonates in a cataclysmic eruption of light. Because this critical mass is always the same, the brightness of the explosion is also always the same. Think of it like a light bulb of a known wattage. If you see a 100-watt bulb looking very dim, you know it must be very far away. By measuring how dim these supernova light bulbs appeared through their telescopes, scientists could calculate exactly how far across the universe they were. And by looking at the color of their light stretched by the expansion of space, they could measure how fast the universe was carrying them away. The goal was straightforward: to measure the deceleration, the gentle braking effect of gravity. The two competing teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, spent years collecting this fragile starlight, painstakingly analyzing each data point. The mood in those observatories and labs shifted from focused anticipation to a growing, bewildering unease. The supernova were not just far away, they were too far away. Their light was fainter than any model of a slowing universe could possibly allow. It was as if you had marked two trees along a straight road, driven away from them for an hour, and then looked back to see they were not just where you left them, but somehow even farther apart than before. The only possible explanation was staggering. The space between those galaxies and us was not just stretching, it was stretching faster and faster over time. The expansion of the universe was accelerating. This was the moment the cosmic floor dropped out. Every instinct in physics screamed that this was wrong. Throw a ball into the air and gravity pulls it back down. Yet here was the universe having thrown everything outward in the Big Bang, and instead of slowing, it was somehow putting its foot on the gas. Something was actively working against gravity, a mysterious, repulsive force woven into the fabric of empty space itself. The discovery was so profound, so counterintuitive, that the researchers themselves doubted their results for months, checking and rechecking for any possible error in their measurements or their understanding of the supernova. But the evidence was undeniable. In 1998, they announced their findings to the world, and cosmology would never be the same. The hunt for the culprit behind this great cosmic acceleration had officially begun. That discovery from the supernova was a shock to the system, but science demands more than a single clue. For a mystery this profound, you need evidence from completely different chapters of the cosmic story. And the universe provided just that in the form of a whisper from its very first moments. This is the cosmic microwave background. Think of it as the oldest photograph ever taken, a snapshot of the infant universe when it was a mere 380,000 years old. At that time, the cosmos had cooled enough from its initial fiery state for atoms to form, allowing light to finally travel freely across space. That first burst of light has been traveling ever since, stretched and cooled by the expanding universe over billions of years into a faint microwave glow that permeates all of space. Today, it's a cold echo just a few degrees above absolute zero, but it holds an incredible secret. Detailed maps of this afterglow, created by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck Observatory, don't show a perfectly smooth blanket of light. Instead, they reveal a subtle pattern of hot and cold spots, tiny ripples in the fabric of the early cosmos. These ripples are not random noise, they are a cosmic blueprint. The precise size and distribution of these temperature fluctuations tell scientists fundamental truth about the shape and content of the entire universe. By analyzing this baby picture, cosmologists could perform a kind of cosmic accounting. They could measure the geometry of space itself. The data delivered a clear verdict: our universe is geometrically flat. Now, what does that actually mean? In a flat universe, parallel lines stay parallel forever, and the angles of a triangle always add up to exactly 180 degrees. This flatness is not a given. It requires a very specific critical density of matter and energy. Think of it like balancing a pencil perfectly on its tip. It requires an exact amount of weight and distribution to achieve that precarious straight line. When scientists added up all the matter they could account for, all the stars, galaxies, gas, and even the invisible dark matter holding galaxies together, the numbers fell drastically short. There simply wasn't enough stuff to make the universe flat. A huge portion of the cosmic budget was missing. The only way the math could work was if the universe contained a vast, smooth, and persistent form of energy, evenly smeared across the vacuum of space itself. This energy, inferred not from exploding stars in the recent universe but from the primordial whisper of its birth, was the same culprit, dark energy. Two completely independent lines of evidence, one from the distant deaths of stars and another from the first light of creation, were pointing at the same invisible force. This convergence turned a shocking possibility into an inescapable reality. The universe was not just expanding, it was being pushed apart by something fundamental to empty space, and we were only beginning to understand its strange properties. So what exactly is this force that is stretching the cosmos? We call it dark energy, but that name is a placeholder for our profound ignorance. It is not a cloud of particles or a hidden sea of matter. It appears to be a fundamental property of space itself, an energy woven into the vacuum. To grasp this strange idea, we need to rethink what empty space truly is. In our daily lives, a vacuum seems like nothingness, a complete absence. But according to quantum physics, the vacuum is far from empty. It is a seething, bubbling arena where pairs of virtual particles spontaneously blink into and out of existence in an endless quantum dance. This vacuum has energy, a baseline hum to the universe. One leading idea is that dark energy is this vacuum energy, the intrinsic cost of having space at all. The irony is that Albert Einstein foreshadowed this concept a century ago, though he rejected it. When he applied his equations of general relativity to the whole universe, he found they predicted a cosmos that was either expanding or contracting. At the time, the static, eternal universe was the prevailing belief. To force his equations to describe a static cosmos, Einstein introduced a fudge factor, a repulsive term he called the cosmological constant. He imagined it as a kind of anti-gravity perfectly balanced against the pull of matter to keep the universe still. Later, when Edwin Hubble discovered the universe was indeed expanding, Einstein famously called the cosmological constant his greatest blunder. Yet today, the accelerating expansion we observe looks exactly like the effect of a cosmological constant. Einstein was right for a reason he never intended. The key to its power lies in a bizarre property, negative pressure. We are used to positive pressure like in a balloon or a tire where pushing outward requires energy. But in the equations of relativity, a medium with strong negative pressure like the quantum vacuum behaves in the opposite way. It creates a gravitational repulsion. Think of space not as an empty stage, but as the stage itself that is actively growing. As the universe expands, more space comes into existence. If each new cubic centimeter of vacuum contains this intrinsic dark energy, then the total amount of repulsive force grows as the universe gets bigger. This is why the acceleration is not just a one-time push. It is a process that gains strength over cosmic time, relentlessly driving galaxies apart. This leading candidate, the cosmological constant, is simple, elegant, and fits the data remarkably well. But it raises a question so profound it shakes the foundations of physics. Why is the strength of this vacuum energy so unimaginably small, yet not zero? The answer to that mystery may lie not in the serene vacuum of today, but in the violent upheavals of the universe's first moments. This constant hum of energy, Einstein's cosmological constant, offers a beautifully simple framework. It suggests that dark energy is not a thing that changes or evolves, but a fixed rule of reality, a number woven into the fabric of the cosmos. The Greek letter lambda, that elegant little symbol, represents a force of empty space so steady and unchanging that its energy density remains constant over billions of years. This leads to a startling implication. As the universe expands and new space is created, the total amount of dark energy increases. It is not being diluted or spread thin, it is accumulating. Imagine a quiet room where the gentle background hum grows louder not because the source changes, but because the room itself is constantly, magically getting larger, adding more of that same hum with every new inch of wall. This is the engine of our accelerating cosmos. The mathematics of this process points toward a future of exponential growth, where the stretching of space feeds on itself, becoming faster and more dominant with each passing eon. In such a universe, the fate of everything beyond our immediate galactic neighborhood is one of deepening isolation. Galaxies not already gravitationally bound to us will see the space between us stretch faster than light can cross it. Their light, stretched into invisibility, will simply fade from the sky. They will vanish over the cosmic horizon, leaving our descendants in a lonely island universe, surrounded by an ever-expanding, ever-darkening void. It is a cold, quiet, and profoundly lonely destiny predicted by an elegantly simple equation. Yet, this very simplicity creates one of the most baffling fine-tuning problems in all of science. The observed value of the cosmological constant is mind-numbingly small. Theoretical predictions from quantum physics suggest the vacuum energy should be up to 120 orders of magnitude larger than what we measure. That is a 1 followed by 120 zeros, a number so colossal it defies comprehension. If the constant were anywhere near that predicted strength, the repulsive force would have been so immense in the early universe that galaxies, stars, and even atoms could never have formed. The fact that it is just the right minuscule value to allow for a cosmos that produced galaxies, planets, and life feels like a cosmic coincidence of impossible precision. It is as if you adjusted a dial with 120 markings, and for the universe to exist as it does, the needle had to land on exactly one specific, nearly invisible mark. This fine-tuning screams that our simple constant might not be the full story. Perhaps lambda is not truly constant after all, but a clue pointing toward a deeper, more dynamic truth hidden within the vacuum. This fine-tuning problem is so severe it feels like a clue we are missing something. The cosmological constant's eerie precision has pushed cosmologists to consider a far more exotic possibility, that dark energy is not a constant at all, but something that changes. The leading candidate in this search is called Quintessence. Picture it not as a static hum, but as a dynamic field, a kind of cosmic weather that ebbs and flows across space and time. Unlike the steadfast lambda, a quintessence field could have been stronger in the past or could weaken in the future. It might even interact subtly with other forces like matter or light in ways we have not yet detected. Some models suggest a truly dramatic future where this field could eventually flip its own properties, switching from a repulsive force driving the universe apart to an attractive one, potentially pulling everything back together in a reversal no one saw coming. This idea transforms dark energy from a fixed rule into an active character in the cosmic story, one with its own history and destiny. But quintessence is not the only path away from lambda. Other theorists question the very framework we are using. Could it be that Einstein's theory of gravity, while perfect for our solar system and galaxies, breaks down on the scale of the entire observable universe? Perhaps we do not need a new energy, but a modification to gravity itself, a tweak to the rules that only becomes apparent across billions of light years. Even more speculative are ideas emerging from string theory, which suggests our universe may be a membrane floating in a higher dimensional space, and the effects we call dark energy are a gravitational echo leaking in from those unseen dimensions. Each of these alternatives is a testament to the profound puzzle before us. The mystery of dark energy is not a small gap in our knowledge. It is a chasm so wide it is forcing a re-evaluation of our most fundamental laws of physics. This vibrant, unsettled state of cosmology is not a sign of failure, but of a field alive with discovery. To choose between these visions of reality, between a constant vacuum and a dynamic field, we need more than elegant equations. We need to catch this phantom in the act, to measure its behavior across the history of the cosmos with unprecedented precision. Catching a phantom requires more than one kind of net. To measure the invisible force that is dark energy, scientists have built a toolkit of cosmic probes, each one peering into a different chapter of the universe's history. We have already seen how distant supernovae act as mile markers and how the cosmic microwave background provides a baby picture. But there is a third, equally crucial method, one that reads the very architecture of the cosmos by listening to its oldest echo. This method is called Baryon acoustic oscillations. To understand it, we need to travel back to the universe's first 400,000 years. At that time, the cosmos was a seething, opaque soup of particles and radiation. In this dense plasma, gravity tried to pull matter together into clumps, but the intense pressure of light pushed back. This created a tug of war, setting up rhythmic sound waves that rippled outward through the hot fluid. When the universe cooled enough for atoms to form, allowing light to escape and creating the cosmic microwave background, those sound waves froze in place, their progress suddenly halted. The result was a cosmic fingerprint, a subtle pattern where matter was slightly more likely to be found at a specific distance from any given starting point. That preferred distance, the size of those frozen sound waves, became a standard ruler etched across the sky. Billions of years later, after gravity has sculpted those early ripples into the vast web of galaxies we see today, that imprint remains. Astronomers can detect it not by looking at individual galaxies, but by mapping the positions of millions of them in enormous three-dimensional surveys. Projects like the Sloan Digital Sky Survey have already done this, charting the cosmos in unprecedented detail. The upcoming Vera-C, Rubin Observatory's legacy survey of space and time, will take this to a new level, observing billions of galaxies over a decade. By statistically analyzing these colossal maps, scientists can measure that standard ruler at different distances, which correspond to different eras in cosmic history. They can ask, how does the apparent size of this ruler change as we look further back in time? Because the ruler's true size is known from the cosmic microwave background, any change in its apparent size directly measures how much the universe has stretched in the intervening eons. It is a direct test of the expansion history, a way to see if dark energy's push has been constant or changing. This is the power of a multi-pronged attack. Supernova give us a direct, if recent, view of acceleration. The cosmic microwave background provides the initial conditions, the starting point of the story. And Baryon acoustic oscillations offer a continuous thread connecting the two, a ruler that measures the stretching of space across nearly the entire lifetime of the universe. By combining the evidence from all three probes, cosmologists are not just guessing at the properties of dark energy, they are triangulating its position in the complex landscape of possible theories. Each new, more precise measurement tightens the constraints, helping to answer the ultimate question: is dark energy the simple, constant hum of empty space, or is it a dynamic phantom field with a story yet to be told? The hunt is on, and the next generation of telescopes is our best chance to finally see the shape of the shadow that has been pulling our universe apart. The geometry of our universe is not an abstract concept, it is the blueprint for our ultimate fate, and the ruler used to draw that blueprint is dark energy itself. The incredibly precise maps of the cosmic microwave background delivered a verdict: our cosmos is flat. This flatness is not a description of shape like a sheet of paper, but of the underlying geometry of space. In a flat universe, parallel lines stay parallel forever, and the rules of geometry we learned in school hold true on the grandest scales. But this condition comes with a strict requirement: the total density of all matter and energy in the cosmos must be exactly at a specific critical value. It is a cosmic balancing act of impossible precision. We now know that nearly 70% of that critical density, the dominant force setting the balance, is the repulsive push of dark energy. This single fact has rewritten the final chapter of our cosmic story. before the discovery of acceleration, cosmologists debated between two other possible geometries, each with its own dramatic ending. A closed universe shaped like the surface of a sphere would have contained enough matter and energy for gravity to eventually win. In that story, the expansion would slow, halt, and reverse, culminating in a fiery collapse known as the Big Crunch. An open universe shaped like a saddle would have expanded forever, but at a steadily slowing, coasting pace, its galaxies drifting apart into a quiet but eternal separation. Our flat universe, however, with dark energy in command, has forged a third destiny, one far stranger than either. Because the energy density of dark energy remains constant as space grows, its influence becomes overwhelming. The acceleration is not a temporary event, it is a new law of cosmic evolution. In this future, the expansion does not just continue, it exponentially accelerates. Galaxies not already bound to us by gravity will see the space between us stretch faster than light can ever hope to cross. One by one, their light will redden, fade, and wink out as they are carried beyond our cosmic horizon. Our local group of galaxies will merge into a single, aging star system, floating in an ever-expanding void of absolute blackness. All distant evidence of a broader cosmos will vanish. This is the fate often called the heat death or the Big Freeze, a state not of fire or ice, but of profound, permanent stillness, where the universe becomes a thin, cold, and silent sea of isolated islands. It is a future shaped entirely by the silent, relentless pressure of the vacuum, a geometry of fate drawn by the hand of a mystery we are only beginning to trace. For nearly 10 billion years, gravity wrote the story of our universe. It was the master architect, the sculptor of cosmic structure. From the faintest ripples in the primordial afterglow, gravity patiently gathered clouds of hydrogen, pulling them into the first stars and the swirling proto-galaxies that would become the grand spirals and ellipticals we see today. Every planet that formed, every solar system that settled into orbit, was a testament to gravity's relentless, attractive pull. In the great cosmic tug-of-war, gravity held the stronger team, its grip on matter firm and unyielding. This force did more than build things, it also acted as a brake on the universe's expansion. Picture throwing a ball straight up into the air. For a moment, it speeds upward, but the entire time, Earth's gravity is pulling back, slowing its ascent until it finally stops and falls. For eons, this was the universe's trajectory, expanding from the initial burst of the Big Bang, but gradually slowing under the collective weight of all its matter. The denser regions where galaxies were forming pulled on the space around them, creating a subtle drag on the entire cosmic expansion. It was a universe under construction, but one destined to eventually coast to a stop. Yet all the while, a silent opponent waited on the other end of the rope. Dark energy, if it behaves like a cosmological constant, possesses a bizarre property. Its energy density does not dilute as the universe grows. While matter spreads thinner and thinner, dark energy's repulsive strength per volume of space remains stubbornly, eerily constant. This created a slow but inevitable shift in the balance of power. About 5 billion years ago, a profound and quiet transition occurred. The universe had expanded so much that matter had become sufficiently dilute. The relentless, undiluted push of dark energy finally matched and then surpassed the weakening pull of gravity. In that moment, the cosmic expansion did not just continue, it began to accelerate. The ball thrown upward instead of slowing suddenly shot faster into the sky. This was the crossover, the point when the fate of the cosmos was sealed not by the clumping of matter, but by the smooth, pervasive pressure of nothingness itself. We can actually observe the echoes of this shift. When astronomers look at the most distant, ancient supernova, they see the universe expanding at a pace consistent with gravity's braking effect. But as they look at closer, more recent stellar explosions, the story changes. The data curves unmistakably upward, telling the tale of acceleration taking hold. This ongoing struggle has a direct, observable consequence for the large-scale structure of the universe. Gravity wants to pull things together, to build ever greater clusters and superclusters. Dark energy, acting as a kind of cosmic tension, works to stretch those bonds and isolate structures. The universe is now in a state where the largest gravitationally bound systems, like our own local group of galaxies, will stay together, but everything beyond that is being carried away on a tide of expanding space that grows faster every day. We are living in the era where the phantom has won, and we are just beginning to see what that victory truly means. The grand architecture of the cosmos is unraveling thread by thread. Look at the deepest maps of the universe, and you will see not a random scattering of lights, but a breathtakingly intricate pattern, a vast cosmic web. This is the largest structure we know, a network of brilliant galaxy filaments tracing paths through immense, dark voids. It is a tapestry woven over billions of years by the patient, relentless hand of gravity, drawing matter together along invisible lines of dark matter. But this masterpiece, once under construction, is now facing a silent, systematic dismantling. Dark energy is not content with merely pushing galaxies apart. It is stretching the very canvas upon which this web is painted. Think of the cosmic web as a delicate lattice of interconnected strings, with dense knots where galaxy clusters reside and vast, empty spaces in between. For eons, gravity worked to tighten those knots and draw the strings closer. Now, a new force is at play. Dark energy acts as a pervasive cosmic tension, pulling on the entire structure from all directions. It is not strong enough to snap the tightest gravitational bonds, the ones holding individual galaxies and even clusters together. Your local galactic neighborhood is safe. But on the grandest scales, the effect is profound and irreversible. The immense voids, those billions of light-year expanses of near-nothingness, are themselves expanding, and they are doing so at an accelerating rate. It is as if the empty spaces in the lattice are being actively inflated, forcing the filaments of the web to stretch longer and thinner. The connections between the great superclusters of galaxies, those majestic intersections in the web, are being pulled taut. Over cosmic timescales, these tenuous bridges will be stretched until they are severed entirely. The result will be a universe of isolated islands. Each gravitationally bound group of galaxies will become its own lonely archipelago, floating in an ever-growing ocean of pure, empty space. The light from any other island will have to cross such an immense and rapidly widening gulf that it will become impossible to see. The cosmic web, that magnificent proof of gravity's unifying power, will fade from view, its connections lost to the accelerating dark. This is not a violent ripping, but a quiet, inexorable thinning, a prelude to the profound isolation that awaits all bound structures in the deep future. The quiet thinning of the cosmic web may only be the prelude to something far more violent. Beyond the steady hum of the cosmological constant lies a theoretical specter so extreme it reshapes our deepest fears about the cosmos. This is phantom dark energy. In this unsettling model, the energy density of dark energy does not remain constant as the universe expands. Instead, it grows. It amplifies itself. Imagine a quiet background hum that not only persists but slowly, inexorably gets louder, its volume knob turned by the expansion of space itself. The consequence of such a runaway force is not a slow freeze, but a definitive and catastrophic end known as the Big Rip. In this scenario, the repulsive force would grow without any natural limit, accelerating the expansion at a ferocious, exponential rate. The timeline collapses from the abstract stretches of eons to a finite, and perhaps measurable, span of cosmic years. First, the phantom energy would tear apart the largest structures that gravity barely holds together. The great clusters of galaxies, those immense cities of stars, would be the first to fly apart as the fabric of space between them stretches faster than their gravitational bonds can withstand. Next, individual galaxies themselves would be shredded. The Milky Way and Andromeda, destined to merge in a distant future under the old rules, would instead be pulled asunder before they could ever touch. The phantom force would then reach into solar systems, prying planets from their stars. It would not stop there. As the acceleration becomes infinite, it would overcome the very forces that hold matter together. In a final, fleeting moment, the bonds within planets would fail, reducing worlds to clouds of dust. Then, the electromagnetic forces holding molecules and atoms together would be overpowered. Finally, in a last violent instant, even atomic nuclei would be torn apart, every particle of matter separated from every other by an infinite stretch of space in a singular, catastrophic event. While our current observations strongly favor the simpler, constant dark energy, the phantom possibility remains a haunting illustration in the equations of theorists. It serves as a dramatic reminder that the dominant component of our universe, this energy of the vacuum we are desperately trying to understand, could in principle harbor a volatility we have not yet witnessed. It asks us a profound question: are we living in a cosmos destined for a long, quiet fade, or one that holds a more decisive and violent final act in its distant future? This staggering mismatch is not a minor puzzle, it is a screaming alarm bell. If dark energy truly is the energy of empty space, the hum of the quantum vacuum, then our two most successful theories of reality are giving us answers that could not be more different. On one side, we have general relativity, Einstein's theory of gravity, and the large-scale structure of the cosmos. It uses the observed acceleration to give us a number for the energy density of dark energy, a tiny, delicate figure. On the other side, we have quantum field theory, the magnificent framework that describes the behavior of particles and forces. When physicists use its equations to calculate the energy inherent in the vacuum of space itself, they get a result. And that result is about 120 orders of magnitude larger than what we observe. To grasp the sheer scale of this error, try to picture a single grain of sand. Now imagine that grain of sand represents the actual, observed strength of dark energy in our universe. The theoretical prediction from quantum physics would be, by comparison, the entire observable universe packed solid with sand. The two numbers are not even in the same galaxy of comprehension. This is the cosmological constant problem, and it is arguably the most severe discrepancy in all of modern science. Such a gulf cannot be explained by a simple miscalculation. It tells us that something is profoundly wrong or profoundly incomplete in our understanding. One possibility is that we are misunderstanding the quantum vacuum itself. Perhaps the frantic dance of virtual particles creates positive and negative energies that somehow cancel each other out with near-perfect precision, leaving behind only the faintest whisper we detect as dark energy. This cancellation would have to be flawless to one part in a number with 120 zeros, a coincidence so astronomically fine-tuned it feels like a miracle written into the laws of physics. Another, more mind-bending possibility arises from theories like string theory and the concept of a multiverse. In this view, our universe is just one bubble in a vast cosmic foam of universes, each with its own random set of physical constants. In most of these universes, the cosmological constant is enormous, and those universes expand or collapse too violently for stars or life to ever form. We, by necessity, find ourselves in one of the rare, freak universes where the constant is almost zero, simply because that is the only kind of universe where beings like us can exist to ask the question. This idea, called the anthropic principle, is controversial because it feels like giving up on a deeper explanation. Yet it underscores the crisis. The cosmological constant problem is so deep that it forces us to consider realities beyond our own. At its heart, this glaring mismatch points to a grander truth. Our theories of the very large general relativity and the very small quantum mechanics are fundamentally incompatible. They have never been successfully married. Dark energy, this smooth, dominant force, may be the key clue that finally leads us to a theory of quantum gravity, a single set of rules that governs everything from the spin of an atom to the fate of the cosmos. Solving this problem would not just explain why the universe is accelerating, it would spark the next great revolution in physics, rewriting our conception of reality itself. Faced with an error of such impossible magnitude, science must consider even the most radical of possibilities. When the numbers defy explanation, perhaps the explanation lies not in a single universe, but in a crowd of them. This is the Multiverse Hypothesis, and it offers a controversial but compelling answer to the fine-tuning of dark energy. The idea is simple in its vastness. What if our cosmos, with its specific laws and its curiously small cosmological constant, is not the only one? What if it is just one bubble in a frothing sea of universes, each with its own random set of physical rules? In this cosmic landscape, the strength of dark energy could be a dial spun at random for each new universe. In the overwhelming majority of these realms, the dial lands on a value that is catastrophically large. In those universes, the repulsive force is so powerful from the very beginning that space expands with such ferocious speed that matter can never clump together. No galaxies condense, no stars ignite, no planets form. They are barren, empty, and silent. In another, much smaller set of universes, the dial lands near zero. Here, gravity dominates completely, often causing a rapid collapse back into a singularity before complex structures can arise. But in an exceedingly rare slice of the multiverse, the dial lands on a value that is not zero, but just right, tiny enough to allow gravity to build galaxies for billions of years, yet present enough to eventually drive an acceleration. According to this line of thinking, we find ourselves in such a universe not because it is special or designed, but because it is one of the very few kinds of universes where observers like us could ever arise to notice it. This is the anthropic principle, a selection effect that reframes our entire existence. We are not at the center of a story written for us. We are the readers who can only exist in a story with certain very specific paragraphs. This perspective is as humbling as it is mind-expanding. It suggests that the hauntingly precise value of dark energy is not a clue to a deeper law waiting to be discovered, but a cosmic lottery ticket we happen to draw. For some scientists, this feels like a philosophical surrender, a step away from the traditional goal of physics to find a unique, elegant explanation for everything. For others, it is a necessary and profound expansion of reality's canvas, one that naturally accounts for the bizarre luck our universe seems to possess. The challenge, of course, is evidence. How do you test for the existence of other universes, realms forever beyond our observational horizon? Some look for potential imprints on our own cosmic microwave background, faint bruises left from long ago collisions with other cosmic bubbles in the multiverse foam. Others see the multiverse as a natural prediction of leading theories like inflation and string theory. Whether it is a true picture of reality or a fascinating thought experiment, the multiverse idea forces us to confront a staggering possibility that the mysterious force determining the fate of all we see might ultimately be a matter of chance in an unimaginably vast cosmic array. To stare into the abyss, we have built new eyes. The mystery of dark energy is not one that will be solved by thought alone. It demands evidence on a scale that matches the cosmos itself. This is the era of the great cosmic cartographers, where international collaborations are launching telescopes and building instruments of staggering precision, all designed to measure the invisible. Their goal is not to see dark energy directly, for it emits no light, but to observe its fingerprints on everything it touches, to map the stretching of space across billions of years with a clarity we have never before possessed. Leading this charge is the European Space Agency's Euclid spacecraft, which began its mission in 2023. Euclid is not a single-purpose instrument. It is a cosmic surveyor equipped with a wide-field telescope designed to peer across 10 billion years of cosmic time. Over its planned 6-year mission, Euclid will construct a 3-dimensional map of the universe, charting the positions and shapes of over 1 billion galaxies. By analyzing this map, scientists will deploy 2 powerful techniques simultaneously. They will measure the Baryon acoustic oscillations, using that frozen sound wave as a standard ruler across cosmic history. At the same time, they will study weak gravitational lensing, the subtle way the gravity of dark matter warps the light from more distant galaxies. This dual approach allows Euclid to cross-check its own findings, providing a robust, independent measure of how dark energy has shaped the growth of cosmic structure. Following closely behind is NASA's Nancy Grace Roman Space Telescope, set to launch later this decade. Named for the pioneering astronomer who paved the way for space telescopes, Roman will act as a wide-eyed explorer. Its field of view will be 100 times larger than that of the Hubble Space Telescope's infrared camera, allowing it to capture vast swaths of the sky in a single glance. This makes it the perfect hunter for distant Type 1, a supernova, those critical cosmic mile markers. Roman is expected to discover thousands of these stellar explosions, building a timeline of the universe's expansion that is both deep in time and rich in detail. It will also perform its own weak lensing surveys, adding another layer to our understanding of how matter, both dark and visible, is distributed and how that distribution is being pulled apart. On the ground, a different kind of effort is already underway. Perched atop a mountain in Arizona, the Dark Energy Spectroscopic Instrument, or DESI, is not a traditional telescope but a complex spectrograph attached to a 4-meter telescope. Its mission is pure cosmic census. It collects the light from tens of millions of galaxies and quasars, not just to see where they are, but to measure precisely how fast they are moving away from us. By obtaining spectra for such an immense number of objects, DESI is creating the most detailed 3-dimensional map of the universe ever made, specifically designed to measure the imprint of Baryon acoustic oscillations with phenomenal statistical power. Each of these projects, Euclid, Roman, and DESI, represents a different angle of attack, a different method to triangulate the truth. They are not in competition, but in concert, a symphony of observation where the data from one will validate and refine the findings of the others. Together, they embody humanity's most ambitious attempt to do something profound, to take the ghostly influence of dark energy and pin it down with numbers, charts, and maps, transforming a philosophical mystery into a quantifiable piece of physics. The light from a distant galaxy is a fragile messenger carrying its story across billions of years of expanding space, but that journey is never a straight line. As the light passes through the universe, it does not travel through empty space. It travels through a landscape sculpted by gravity. Every galaxy cluster, every strand of dark matter, every pocket of invisible mass bends the fabric of space-time, and light must follow those curves. This phenomenon is called gravitational lensing, and it provides a way to see the invisible architecture of the cosmos. In its most dramatic form, strong gravitational lensing, the distortion is obvious, creating multiple images of a single quasar or stretching a background galaxy into a brilliant, luminous arc around a foreground cluster. But for the study of dark energy, a far more subtle effect holds the key: weak gravitational lensing. Here, the distortions are not visible to the eye in a single image. No galaxy is turned into a ring or duplicated. Instead, the shapes of millions upon millions of distant galaxies are ever so slightly sheared, stretched from their true circular forms into faint, coherent ellipses, all aligned by the gravitational pull of the matter that lies between them and us. It is as if you are looking at a field of distant streetlights through a gently warped pane of glass. Individually, each light looks normal, but when you step back and analyze the entire pattern, you can detect a systematic twist in their orientations, revealing the imperfections in the glass. Astronomers perform this analysis on a cosmic scale by using powerful telescopes to capture the shapes of countless galaxies. They can perform a statistical census of distortion. This allows them to create a three-dimensional mass map of the universe, charting not just the luminous galaxies we see, but the vast, unseen scaffolding of dark matter that holds them together. This map is a historical record because light from more distant galaxies has traveled longer. It has passed through more of the universe's evolving structure. By comparing the weak lensing signal from galaxies at different distances, scientists can essentially make a movie of how matter has clumped together over cosmic time. And this is where dark energy enters the picture. Remember, gravity wants to pull matter into denser clumps, building the cosmic web. Dark energy, with its repulsive push, works against this, stretching space and suppressing the growth of these large-scale structures. By measuring exactly how much matter has clumped over the history of the universe, weak gravitational lensing gives us a direct readout of the strength of dark energy's opposition. It measures the shadow of the phantom's work. A stronger, more aggressive dark energy would have left the cosmos more smooth, with matter less gathered into filaments and clusters. A weaker dark energy would have allowed gravity to build even grander structures than we see. The subtle, statistical twist in the shapes of billions of galaxies is therefore a whisper from the vacuum itself, telling us how it has been wrestling with gravity for the fate of everything. This technique, combined with supernova and Baryon acoustic oscillations, forms the third pillar of our investigation, turning the distortion of light into a precise scale for weighing the invisible force that is pulling our universe apart. That subtle twist in starlight is not our only way to listen to the universe. There is another, older echo, a rhythm frozen into the very distribution of galaxies. To understand it, we must return to the universe's first moments, when it was not dark and quiet, but a seething, roaring sea of energy. For the first 380,000 years, the cosmos was a thick, opaque soup. Ordinary matter existed as a plasma of protons and neutrons, known collectively as baryons, and they were inextricably tangled with a blinding bath of light with photons. In this dense, hot fluid, gravity was already at work, trying to pull matter together into denser clumps, but it faced a powerful opponent, pressure. The intense radiation of the early universe pushed back with tremendous force against gravity's inward pull. This created a cosmic tug-of-war, a push and pull that set the entire medium ringing like a struck bell. From every slightly denser region, a spherical pressure wave rippled outward through the hot plasma. You can think of it as a sound wave, a deep, resonant boom propagating through the primordial fluid. These waves traveled at a significant fraction of the speed of light, carrying matter along in a shell at their leading edge. For nearly 400 millennia, this symphony of pressure and gravity played out, with sound waves racing through the infant cosmos. Then everything changed in an instant, cosmologically speaking. The universe expanded and cooled enough for a pivotal event, recombination. Electrons combined with protons to form the first neutral hydrogen atoms. Suddenly, the photons, which had been constantly scattering off the charged particles, were set free. They decoupled from matter and streamed outward in every direction, becoming the cosmic microwave background we detect today. For the sound waves, this was like the music stopping mid-note. The pressure from the radiation vanished instantly. The waves froze in place, their progress suddenly and permanently halted. The result was a cosmic fossil. Each wave left a spherical shell of matter, a ripple where particles had been gathered by the passing pressure front, now frozen at a very specific distance from the original over-dense seed. That distance, the distance the sound could travel before the music stopped, became a standard ruler. Its size is imprinted on the sky, a preferred scale of about 500 million light-years. This is the imprint of Baryon acoustic oscillations. For billions of years, gravity continued to work, pulling more matter into those frozen ripples and sculpting them into the galaxies and clusters we see. But that original pattern, that subtle preference for galaxies to be separated by that specific scale, remained etched into the large-scale structure of the cosmos like a watermark. We cannot see it by looking at any two galaxies. Instead, we find it by performing a cosmic census, by mapping the precise three-dimensional positions of millions of galaxies in enormous surveys. Astronomers can perform a statistical analysis. They look at the probability that any two galaxies are separated by a given distance, and in that data, a clear signal emerges, a slight excess, a statistical peak, showing that galaxies are indeed more likely to be found separated by that magic scale of 500 million light-years. It is the ghostly fingerprint of those ancient sound waves. This is why BAO is such a powerful tool. We know the true size of this ruler from the cosmic microwave background, from that baby picture of the universe. When we look out at galaxies from different eras, we are looking at this ruler at different points in cosmic history. If we see that the ruler appears smaller than expected, it tells us the universe had not expanded much when that light was emitted. If it appears larger, it means space had stretched considerably. By measuring this apparent stretching of the standard ruler across cosmic time, we get a direct, clean history of the expansion rate. It is like having a series of calibration marks placed throughout the universe's timeline, allowing us to measure exactly how much dark energy has been stretching the fabric of space between each mark. This method beautifully complements the others. Supernova give us brilliant, individual flashes that mark expansion. Weak lensing shows us how structure growth was suppressed. But BAO gives us a steady, statistical heartbeat, a rhythm from creation that allows us to take the universe's pulse across nearly its entire lifetime, tightening the constraints on our phantom until it has nowhere left to hide. But just as we build our most precise maps, a crack has appeared in the very foundation of our cosmic model. The universe's current expansion rate, a number called the Hubble constant, is something we should be able to measure with confidence. It is the speed at which galaxies are flying apart from us right now. For decades, astronomers have refined two primary methods to pin down this number, and they are now in stubborn, persistent disagreement. The first method looks back to the dawn of time, using the exquisite detail of the cosmic microwave background. By analyzing the patterns in that ancient light, scientists can run the cosmic film backward, using our well-tested model of physics to calculate what the expansion rate must be today. That method gives us a very precise answer. The second method looks at our local cosmic neighborhood, using celestial lighthouses like Cepheid variable stars and Type 1a supernova to measure distances and recession speeds of nearby galaxies directly. This approach is like using a radar gun on the cosmos, giving us a direct readout of the current expansion, and it consistently gives a number that is significantly faster. This discrepancy is known as the Hubble Tension, and it is not a small statistical fluke. The two values disagree by enough that the probability of it being a simple error is vanishingly small. It is as if you calculated how fast a car should be going based on its acceleration from a complete stop, and then used a speedometer to measure its actual speed, and the two numbers disagreed in a way that no margin of error could explain. This tension suggests a profound possibility that our standard model of cosmology, the very framework that includes dark energy as a simple constant, might be missing a crucial piece. One tantalizing explanation points directly at the phantom itself. What if dark energy is not perfectly constant? What if it evolved or changed strength in a way our simple models do not account for? A dynamic dark energy could have subtly altered the expansion history, making the early universe's prediction for today's rate incorrect. Other theories look to the first moments after the Big Bang, proposing exotic forms of early radiation or new types of subatomic particles that would have shifted the primordial conditions just enough to throw off the modern calculation. The Hubble tension is more than a technical problem for astronomers. It is a tremor running through our understanding of cosmic history. It tells us that the mystery of dark energy is not a settled chapter, but an unfolding story where even our most basic assumptions are being questioned. If the numbers from the beginning of time and the numbers from today do not match, then something in the story we are telling about what happened in between is wrong. And that something is likely tied to the invisible force that fills the void. We are living in a brief and brilliant window of cosmic history. To understand our place in this grand story, we can chart the timeline of dark energy's rule, a narrative that stretches from the fiery birth of everything to a future of profound stillness. For the first 9 billion years after the Big Bang, the universe was a realm defined by matter. Gravity held the pen, writing a story of construction. Galaxies swirled into being, stars ignited in vast nurseries, and the great cosmic web slowly gathered its threads. All the while, the universe was expanding from its initial burst, but that expansion was steadily slowing, like a great wheel gradually losing its spin under a constant, gentle brake. This was the age of structure, a luminous era of becoming. Then, roughly 5 billion years ago, a silent transition occurred. The universe had grown so vast that matter, its particles spread thinner and thinner, saw its density fall below the constant, unwavering density of dark energy. Imagine two runners on an endless track. For eons, the runner named matter was in the lead, but their speed was fading with every step. The runner named dark energy maintained a perfectly steady, relentless pace. 5 billion years ago, dark energy finally pulled ahead. In that moment, the cosmic expansion did not just continue, it began to accelerate. The great wheel was no longer slowing down, something had begun to push it faster. We have crossed into the age of dark energy, an era where the vacuum of space itself dictates the destiny of the cosmos. And this new ruler's influence is only growing stronger with time. Looking ahead, the timeline unfolds toward a quiet and inevitable conclusion. In about 100 billion years, a span almost 10 times the current age of the universe, the acceleration will have carried all galaxies outside our immediate local group beyond our cosmic horizon. Their light, stretched to infinitely long wavelengths, will simply fade from the sky. The universe, as seen from any surviving point within our galactic neighborhood, will become a much smaller place. Fast forward to 1 trillion years from now, and the scene is one of profound isolation. The universe will be cold, dark, and largely empty. The afterglow of the Big Bang will have redshifted into complete undetectability. Any civilization that persists will gaze out upon a cosmos containing only the stars of its own merged galactic home, an island of fading warmth in an endless, black, and silent sea. This timeline is not a prophecy of doom, but a map of physical inevitability. It frames our present moment with startling clarity. We exist in a fleeting golden hour, a luminous sliver of time after the stars have lit up but before the curtains of space have fully closed. We are privileged to see a universe filled with galaxies, to trace the cosmic web, and to sense the mysterious force that is writing its final chapters. Our brief window of observation is what makes the mystery of dark energy so urgent and so profound. This cosmic timeline presents us with a stark and beautiful truth that we are temporary guests in a house that is slowly dissolving around us. The discovery of dark energy does more than rewrite a physics textbook. It forces a deep philosophical shift. For centuries, human thought often placed us at the center of a narrative, whether divinely ordained or as the pinnacle of a grand evolutionary story. The accelerating universe dismantles that comforting notion with quiet, impersonal force. We are not the purpose of this vast expanse. We are a brief and brilliant afterthought, a fleeting phenomenon that has arisen in a narrow slice of cosmic time between the age of structure and the age of isolation. Our entire history, from the first life on Earth to the launch of our telescopes, is but a flicker in a universe destined for a cold, silent, and endless expansion. This can feel like a profound existential chill, the ultimate lesson in insignificance. All our monuments, our art, our civilizations, even the very evidence of the universe's fiery birth in the cosmic microwave background, will one day fade from any possible view. What, then, is the point of striving, of building, of seeking to understand? The point may lie precisely in the asking. As the astrophysicist Janna Levin has eloquently noted, we are living in a privileged era of cosmic transparency. For a mere sliver of the universe's lifespan, the conditions are just right for creatures like us to look up, to see the afterglow of creation, to trace the web of galaxies, and to detect the shadow of the force that will end it all. This window is closing, but we are here while it is open. This perspective transforms our quest from one of seeking a permanent place in the cosmos to one of bearing witness. Finding meaning shifts from the hope of an eternal legacy inscribed in the stars to the profound act of comprehension itself. In a universe that is fundamentally transient, the act of understanding its story, of mapping its grandeur and unraveling its deepest mysteries, becomes its own kind of sacred purpose. It is a celebration of consciousness in a cosmos that is mostly unconscious, a defiant spark of curiosity in the face of an inevitable dark. This is not a reason for despair, but a call to awe. Our temporary nature makes this moment of awareness all the more precious. It urges us to look deeper, to ask bigger questions, and to appreciate the incredible luck of our existence in this golden hour of cosmic history. The value is not in the permanence of our mark, but in the depth of our gaze while the light still shines. The name itself is a source of confusion. Dark energy sounds like a sinister power or a hidden substance, but these images lead us astray. To truly grasp the mystery, we must first clear away what it is not. Most importantly, dark energy is not dark matter. Though they share that shadowy adjective, they are opposites in almost every way. Dark matter is a ghostly form of matter. It clumps together under gravity, acting as the invisible scaffolding that holds galaxies and clusters intact. We detect it by the gravitational pull it exerts on the stars and gas we can see. Dark energy, in stark contrast, is not matter at all. It does not clump. It is perfectly smooth, a uniform presence that fills every cubic centimeter of the vacuum, and its effect is not to pull things together, but to push them apart on the grandest scales. They are two different answers to two different cosmic questions. Dark matter explains why galaxies hold their shape, while dark energy explains why the space between galaxies is growing faster every second. It is also not anti-gravity in the science fiction sense. You will not find a dark energy device that lets you float off the ground or reverses the orbit of a planet. That kind of localized, targeted reversal is not what is happening. Dark energy's repulsive effect is a cosmological phenomenon, a subtle property of empty space that only becomes significant when you add up its influence across billions of light years. On the scale of a solar system or even a galaxy, gravity's pull is overwhelmingly dominant. The repulsion only wins in the vast, near-empty stretches between galactic clusters where gravity's grip is already tenuous. This leads to another key point. Dark energy is not a force carried by a particle like light is carried by the photon. We have no dark energy particle in our standard model. Instead, it is better understood as a condition of space itself, a kind of tension or energy density inherent to the vacuum. This is why we often describe it as a property, not a thing. Finally, and this is critical, dark energy is not yet proven to be Einstein's cosmological constant. That constant, represented by the Greek letter lambda, is our leading and simplest explanation, a fixed energy of the vacuum. But it remains a hypothesis, a candidate. Dark energy is the name we give to the observed phenomenon, the measured acceleration of the universe's expansion. Lambda is one proposed solution to what dark energy could be. By separating the observation from the explanation, we keep our minds open to the thrilling possibilities, whether it is a constant hum, a dynamic field called quintessence, or something even more unexpected. Dispelling these myths is not just about technical accuracy, it sharpens our focus. It strips away the science fiction aura and brings us face to face with the raw, elegant mystery, a fundamental feature of reality that we have detected but do not yet understand. The universe cannot be recreated in a lab, but we can build a digital twin. Since we cannot run experiments on the cosmos itself, cosmologists have turned to some of the most powerful machines ever built, supercomputers. These are our virtual laboratories where we can test the influence of dark energy across billions of years in a matter of weeks. The method relies on what are called n-body simulations. Imagine starting with a digital box that represents a vast chunk of the early universe. You fill it with billions, even trillions of simulated particles, each one representing a clump of dark matter. Their starting positions are not random. They are seeded with the exact same tiny ripples we see in the cosmic microwave background, that ancient baby picture of the cosmos. Then you press play. The simulation applies the known laws of physics, primarily gravity, and lets time run forward. Over millions of computational steps, those particles begin to move, pulled by their mutual attraction. They slowly coalesce into halos, which become the seeds for galaxies, and those halos themselves gather along filaments, weaving the immense cosmic web around growing voids. This is how we watch a universe grow from a smooth whisper to a structured tapestry, entirely inside a machine. Pioneering projects like the Millennium Simulation first charted this virtual evolution, but today's efforts, like the Flamingo simulations, are orders of magnitude more complex. They incorporate not just dark matter and gravity, but the messy physics of ordinary matter, the heating and cooling of gas, the explosive feedback from supernova and black holes. It is a staggering computational challenge, requiring thousands of processors working in concert for months. But the true power of these virtual universes lies in their flexibility. Scientists can run the same simulation multiple times, each time tweaking a single fundamental rule, the behavior of dark energy. In one run, dark energy is a perfect cosmological constant, that steady hum. In another, it is a dynamic quintessence field, stronger in the past. In a third, it is the terrifying phantom energy that grows with time. Each version of the simulation produces a different cosmic web. A stronger early dark energy might suppress the growth of clusters, leaving the universe smoother. A phantom energy could stretch the filaments thinner, faster, creating a more ragged web. Once these digital universes are complete, researchers hold them up against the real thing, comparing the simulated patterns of filaments, voids, and clusters to the actual maps being created by telescopes like Euclid and Daisy. It is a cosmic matching game, which simulated web looks most like the one we actually live in. This process turns abstract equations into testable predictions. We are not just imagining what dark energy does, we are watching it shape entire virtual cosmoses, giving us a crucial lens to interpret the faint signals from our own. This fine-tuning is not the only eerie alignment we must explain. There is another, more temporal puzzle known as the coincidence problem. For nearly the entire history of the universe, the cosmic budget was dominated by a single component. In the first few 100,000 years, radiation ruled, an intense bath of light that dictated the expansion. For the next 9 billion years, matter was king, with its gravitational pull shaping galaxies and slowing the cosmic expansion. Dark energy existed all the while, but its influence was utterly negligible, a whisper drowned out by the roar of matter and radiation. Only in the relatively recent cosmic past, about 5 billion years ago, did the density of dark energy rise to become roughly equal to the density of matter. And now, in our present epoch, dark energy has taken the lead and begun its accelerating reign. The window of time in which these two titanic forces are of comparable strength is cosmologically brief, a fleeting moment in a 13.8 billion year story. Yet here we are, conscious observers, alive in that exact sliver of time. This feels like more than luck. It is as if you walked into a vast, empty theater that has been dark for centuries, flipped the light switch, and discovered the single, one-hour play was just reaching its climax as you took your seat. The timing is suspiciously perfect. Why now? Is this profound coincidence simply a bizarre accident of cosmic timing? Or does it point to a hidden relationship we have not yet seen? One compelling line of thinking brings us back to the anthropic principle. If a universe must have a matter-dominated era long enough to form stars, planets, and life, and if dark energy eventually always becomes dominant, then observers will, by necessity, arise around the crossover period. We could not exist in the first fiery moments of radiation dominance, nor in the far future of dark energy's lonely isolation. We can only find ourselves in the transitional era, making the coincidence a selection effect, not a designed event. Yet many physicists find this answer unsatisfying, a philosophical stop sign placed before a deeper truth. They search for a physical mechanism that would link the two eras, making the crossover not a random occurrence but a natural phase transition in the life of the cosmos. This is where ideas like coupled quintessence gain traction. In these models, dark energy is not a passive background field. It actively interacts with matter, perhaps exchanging energy in a subtle dance across cosmic time. This interaction could act as a cosmic regulator, ensuring that as matter dilutes with expansion, the dark energy field evolves in a synchronized way, making the epoch of equality a predictable and inevitable milestone rather than a freak accident. Solving the coincidence problem would do more than tidy up a quirk in the timeline. It would force a revolutionary shift in our cosmic picture. Right now, in our standard model, dark energy, dark matter, and ordinary matter are treated as separate, independent ingredients in a cosmic soup, each following its own rules. If the coincidence points to a direct connection, it suggests these components are not independent at all. They could be different manifestations of a single, underlying substance, or different phases of a unified field, interacting in ways that choreograph the universe's evolution from beginning to end. Unraveling this temporal riddle might be the key that finally shows us how the pieces of the cosmos truly fit together. This pursuit leads us to the very edge of what we can know. Our tools of understanding, the laws of physics we have so carefully crafted, were born here on Earth. They were forged in laboratories, tested in particle colliders, and confirmed by observing planets and stars within our relatively calm galactic neighborhood. They are rules written for a specific theater, one of moderate energies, strong gravity, and space that does not stretch noticeably during an experiment. Dark energy is a phenomenon of an entirely different stage. It is a property of the vacuum itself, acting across tens of billions of light years, and its true nature may be inextricably linked to realms of physics we have only dreamed of, like a complete theory of quantum gravity or the hidden geometries of string theory. These are domains where our current concepts of space, time, and cause and effect may break down or transform into something unrecognizable. Consider the possibility that the final answer does not fit into a neat, intuitive picture. It might exist as a set of elegant but profoundly abstract equations, a mathematical truth about the universe that lacks any analogy to our everyday experience. Our minds evolved to solve practical problems in a world of medium-sized objects, to avoid predators, build shelters, and understand the arc of a thrown rock. We are exquisitely adapted to what the biologist Richard Dawkins called the middle world, the sheer alien scale of the cosmos, and the bizarre rules that may govern its foundation could be concepts our cognitive architecture is simply not built to visualize in a familiar way. This is not a statement of defeat, but a necessary and profound humility. It reframes our quest from a straightforward puzzle to be solved into a heroic expansion of the possible. The value lies not only in a final answer we may never reach, but in the journey itself, in the gradual, relentless pushing outward of the boundary between the known and the unknown. Every precise measurement from a new telescope, every daring simulation on a supercomputer, every elegant but untested theory, represents humanity reaching as far into the dark as our reason and imagination can possibly extend. The mystery of dark energy, therefore, becomes more than a scientific question. It is a mirror held up to our own capacity for understanding, challenging us to see how far into the grandest truths of reality our species can truly see. This grand mystery belongs to everyone. The quest to map dark energy is not a closed door reserved for a handful of scientists in remote observatories. It is a story unfolding in public view, and you can be a part of it. For over a decade, projects like Galaxy Zoo have demonstrated the incredible power of collective curiosity. They invite anyone with an internet connection to look at stunning images of distant galaxies captured by robotic telescopes and answer a simple question: is this galaxy a spiral or an ellipse? This seemingly simple act of pattern recognition is something the human brain excels at, but that even our best algorithms can struggle with consistently. Millions of classifications from hundreds of thousands of volunteers have created a foundational map of the cosmos, data that is directly used by researchers to understand how galaxies form and how they are distributed across the vast cosmic web. This is citizen science at its best, turning a global community into a single, powerful instrument for discovery. The potential extends far beyond galaxy shapes. The subtle light curves of distant supernova, the very data that revealed acceleration, need careful scrutiny to separate true signals from cosmic imposters. The search for the faint, telltale arcs of gravitational lenses, those warped images that map invisible dark matter, requires scanning petabytes of sky images for rare and beautiful anomalies. These are all tasks where trained human eyes, even amateur ones, can spot what machines might miss, as the next generation of telescopes like Euclid and the Vera C. Rubin Observatory comes online. They will not just collect data, they will unleash a flood of it, a deluge of cosmic information on a scale we have never before managed. Processing this avalanche will demand new kinds of intelligence, both artificial and human. This is where open-source collaboration enters the stage. Programmers, data scientists, and curious students around the world participate in hackathons and collaborative coding projects, developing the sophisticated algorithms needed to sift this digital universe for clues. They are building the tools that will find the needles in the cosmic haystack. Beyond direct participation, the story of dark energy is being told in planetariums, through gripping documentaries, and in free online courses from universities worldwide. These platforms do more than inform, they create a shared sense of wonder and collective endeavor. When you learn about the accelerating universe, you are not just a passive observer, you are bearing witness to one of the most profound discoveries in human history. You become part of the chain of curiosity that stretches from a person classifying a galaxy on a home computer to a team of cosmologists running a simulation on a supercomputer. In a cosmos that often emphasizes our smallness, this shared pursuit offers a powerful counterpoint, a reminder that our collective desire to understand is a luminous thread connecting us to the universe itself. The search for an invisible force does more than chart the cosmos, it reshapes our world, pursuing a question as profound as dark energy with no obvious practical goal might seem like a purely philosophical exercise. Yet history shows that when humanity reaches for the stars, the tools we build to get there often transform life back on Earth. The drive to map the accelerating universe has become a powerful engine for technological innovation, spinning off advances that touch medicine, communication, and the very way we process information. To see the faintest galaxies, we needed to reinvent the eye of the telescope. Modern sky surveys demand digital camera sensors of unprecedented sensitivity and scale. These are not ordinary cameras, they are feats of engineering that can capture single photons with minimal noise across vast swaths of the sky. The same core technology that allows the Euclid spacecraft to measure the subtle shapes of billions of galaxies is now refining medical imaging devices, enabling earlier and more precise detection of illness through clearer scans with lower radiation doses. The challenge of transmitting this river of data from orbit to supercomputers on the ground pushes the boundaries of data compression and laser communication, technologies that eventually strengthen the backbone of our global telecommunications networks. But the innovation extends far beyond hardware. The true deluge is in the data itself. A single night at an observatory like the Vera C. Rubin facility can generate more raw information than was contained in the entire Library of Congress just a few decades ago. Making sense of this requires new kinds of intelligence. Astronomers, collaborating with computer scientists, have pioneered sophisticated algorithms to find patterns in this chaos, to separate signal from cosmic noise, and to train machines to classify celestial objects automatically. These techniques are the direct ancestors of the machine learning and big data analytics that now power everything from weather prediction and financial modeling to the development of new medicines and smarter cities. The quest itself becomes a classroom without walls. There is a profound human dividend to this exploration. The grand mystery of dark energy, the stunning images of nebulae and galactic collisions, these are not just scientific data, they are stories. They capture the imagination of a young student gazing at a planetarium show, or a teenager tinkering with code to help classify galaxies online. That spark of wonder is a critical catalyst. It inspires generations to pursue careers in science, technology, engineering, and mathematics. The physicists and astronomers working on dark energy today will be joined tomorrow by engineers who first dreamed of space, by programmers who cut their teeth on open-source cosmology projects, and by problem solvers who learn to think on cosmic scales. This pipeline of talent and curiosity is perhaps the most valuable spin-off of all. So while knowing why the universe is accelerating may not build a better refrigerator or a faster car in the immediate sense, the relentless effort to find out builds something far more enduring. It cultivates a culture of international collaboration as scientists across continents share data and ideas. It drives cutting-edge innovation at the intersection of disciplines. And it fosters a deeper, more humble appreciation for our place in a vast and mysterious cosmos, reminding us that the act of seeking understanding is itself a noble and profoundly practical human endeavor. The coming decade is not just another chapter in this story, it is the moment we turn the page. The great cosmic cartographers have deployed their tools, and now we must listen. The floodgates are opening, and a torrent of data is beginning to pour in from the Euclid spacecraft, the Dark Energy Spectroscopic Instrument, and soon the Nancy Grace Roman Space Telescope and the Vera C. Rubin Observatory. These are not isolated experiments, they are a synchronized global campaign, a multi-billion-dollar investment with a single, breathtaking goal to finally see the shape of the shadow. Their combined observations will measure the stretching of the universe and the growth of its structure with a precision we have never before dreamed possible. This precision is aimed at one specific number, a value physicists call W, the equation of state parameter. Think of W as the identity card for dark energy. It tells us how its pressure relates to its energy density. For a simple, constant vacuum energy, Einstein's cosmological constant, this number is exactly -1. It is a fixed point, a signature of a static, unchanging force. But if dark energy is something dynamic, like a quintessence field that evolves over time, then W would deviate from -1. It might be slightly different, and that tiny difference would change everything. The missions of this decade are designed to measure W2 within 1% precision. They are essentially taking a cosmic fingerprint with such fine detail that we will be able to see if it matches the smooth, unchanging pattern of a constant, or if it reveals the unique swirls and walls of a living, changing field. A confirmed deviation from -1 would be more than a new discovery, it would be a revolution. It would mean dark energy has a history, a personality. It could be growing stronger or fading away, interacting with other forces, or perhaps even preparing for a future transformation we cannot yet foresee. Such a result would instantly invalidate our simplest model and send theorists rushing back to their chalkboards with the most exciting problem imaginable. Conversely, if all this exquisite data firmly pins W to -1, it solidifies the cosmological constant as a fundamental rule of reality. It would mean the vacuum energy is indeed a perfect eternal hum, and the strange fine-tuning we observe is not a clue to deeper dynamics, but a bizarre, permanent feature of our universe. Either outcome reshapes our understanding of existence. We are living in the decade where the phantom, after a century of hiding in the equations, finally steps into the light to have its picture taken. The exposure is set, the lens is focused, and the image is developing before our eyes. The phantom's influence extends far beyond the telescope's lens. Dark energy refuses to be confined to the domain of cosmology alone, spilling over into a dozen other fields of human thought and demanding a conversation that spans the entire spectrum of intellectual pursuit. This is not a solitary mystery, it is a gravitational lens for inquiry itself, pulling together perspectives from across the scientific and philosophical landscape to focus on a single, profound unknown. Particle physicists, for instance, are deeply invested. They are the architects of the quantum vacuum, the very arena where dark energy may reside. They work to model potential quintessence fields, asking if new, ultra-light particles or forces could be the source of this smooth, repulsive pressure. Their massive colliders, built to probe the highest energies, are testing the fundamental rules that might one day explain the lowest energy phenomenon we have ever detected, the gentle push of empty space. Meanwhile, string theorists explore vast mathematical landscapes of possible universes, each with its own set of physical constants. Their work provides a potential framework for the multiverse, a cosmic context where the eerie fine-tuning of dark energy might not be a miracle, but a statistical inevitability across an infinite ensemble of realities. This abstract mathematical exploration requires new tools, which is where another discipline enters, data science and advanced mathematics. The torrent of information from new sky surveys is a universe of numbers in itself. Mathematicians and computer scientists develop sophisticated new algorithms to sift through petabytes of imaging data to find the subtle statistical signals of Baryon acoustic oscillations and to map the invisible dark matter web through weak gravitational lensing. They are building the analytical machinery to see the phantom's shadow in the noise. And then there are the philosophers, whose ancient questions about our place in the cosmos have been given startling new urgency. They grapple with the implications of the anthropic principle, asking what it means for our existence if the fundamental constants of nature appear fine-tuned for life. Does a multiverse explain our lucky draw, or does it simply relocate the mystery? The discovery of acceleration forces a re-examination of concepts like eternity, destiny, and the nature of nothingness itself. Even the arts are responding to this new cosmic narrative. Visual artists create installations that evoke the isolation of the Big Freeze, while writers and filmmakers craft stories set in the deep future of an accelerating universe, exploring the psychological and social implications of a cosmos coming apart. This cross-pollination is not a side effect, it is the hallmark of a true scientific revolution. When a question becomes deep enough, it transcends its original discipline. Dark energy demonstrates that the largest mysteries cannot be solved from a single vantage point. They require the physicist's equation, the mathematician's model, the philosopher's question, and the artist's vision, all converging to illuminate a darkness that is, for now, greater than any one field of light. You might wonder what a force billions of light years away has to do with the rhythm of your daily life. The connection is not in a practical gadget, but in the story we tell ourselves about existence. For thousands of years, human cultures looked up at the night sky and saw permanence. The constellations were fixed, the heavens an eternal, unchanging stage upon which the brief drama of life played out. Stories spoke of celestial cycles that repeated forever. We now know that stage is not still. It is moving, growing, and being actively stretched by a hidden hand. The universe had a fiery beginning. It has a life story of structure and change, and its final chapters are being written by this dark energy. To learn this is to participate in the oldest and grandest human project, the quest to understand our place in the grand scheme of things. Where did we come from? Where are we going? These are not just scientific questions, they are the bedrock of meaning. Knowing that the cosmos evolves, that it is not a static backdrop but a character in its own epic, fundamentally changes our relationship to it. This knowledge cultivates a specific kind of awe, one tinged with a profound humility. It reminds us that reality, at its most fundamental level, is far stranger, more vast, and more mysterious than our ordinary experience could ever suggest. In a world that often pulls our attention to the immediate, the urgent, and the narrowly personal, contemplating dark energy offers a radical shift in perspective. It connects the quiet moments of your life to the deepest currents of time and space. It grounds you by revealing your true, small scale in an accelerating cosmos. Yet it liberates you by revealing that you are part of a conscious species capable of perceiving that very acceleration. You are living in the fleeting moment when the universe can be known, and that is a story worth being part of. Our journey through this mystery reveals a universe far more dynamic and enigmatic than we ever imagined. We began with a cosmic story everyone thought they knew, a grand expansion slowly winding down under gravity's gentle break. Then, a flicker of distant starlight betrayed the truth. The universe is not slowing at all, but accelerating, pushed apart by a silent force woven into the fabric of empty space itself. We traced the evidence from the ancient whisper of the cosmic microwave background to the vast, statistical heartbeat of Baryon acoustic oscillations, each independent clue pointing to the same invisible culprit. We confronted the leading suspect, Einstein's cosmological constant, a steady hum from the quantum vacuum that promises a future of cold, lonely isolation as galaxies vanish over the cosmic horizon. Yet the story grows stranger still. The haunting possibility of phantom energy whispers of a more violent end, while the staggering fine-tuning of the numbers and the stubborn Hubble tension suggest our simplest answer may be incomplete. These are not minor puzzles, they are tremors running through the foundation of physics itself, hinting that dark energy could be a dynamic field, a modification of gravity, or even a sign of realities beyond our own. This quest is far more than a technical problem for cosmologists. It is a fundamental human exploration, a collective act of bearing witness during a brief, brilliant window of cosmic history. We exist in the narrow sliver of time after the stars have lit up but before the accelerating dark has fully closed the curtains. Our privilege is to see a universe filled with galaxies and to sense the mystery writing its final chapters. The next generation of telescopes from Euclid to Roman are not just instruments, they are extensions of our curiosity, poised to take the phantom's fingerprint with unimaginable precision. They will tell us if the hum is truly constant or if it has a story yet to be told. So as you look up at the night sky, remember you are gazing into an epic that is still being written, on a canvas that is stretching faster every second. This great cosmic detective story belongs to all of us. What do you think dark energy truly is? Share your thoughts on this profound mystery below. Subscribe for more journeys to the edge of understanding, and always keep looking up.